So, hello everyone. I hope I'm audible. So, I welcome you all to this live interaction session for the course Introduction to Abstract Group Theory. So, let me just share my screen. I hope that it's visible. Okay. Uh, so if you have any doubt from the week 4 practice assignment or lecture notes, then you can ask. Otherwise, we will start discussing the solution for assignment 1 as the last date is over for that assignment, so we can discuss that solution. So if there is any doubt, then you can ask.
There is no doubt, sir.
Hello, I can't hear. Can you just repeat?
I said that there's no doubt.
Okay, so let me just share then the first problem of assignment 1. If you know the solution, then you can also help me in discussing the solution. We will build upon your inputs. So here is the first problem, which asks which of the following sets G with the indicated binary operations are groups. First one is G is the set of all non-zero rational numbers, and the operation is given by A star B, which is 2AB. So it's not a usual multiplication of non-zero rational number. We are just scaling the usual multiplication by 2. So will it be a group now? So first of all, is it a binary operation? Although it's given that all the operations are binary operation, but we should also check whether they are binary operations. So can tell me whether the first one is a binary operation. So G is Q star and two elements are composed using this multiplication rule 2AB. Okay. So definitely for any two non-zero rationals A and B, 2AB is also a rational, non-zero rational. So the G is closed under this operation. So clearly star is a binary operation. Also star is associative. Since the multiplication is associative, now what is the identity? So for identity, we can check uh, if A star E is A for all. The other one we should also write E star A for all A belongs to the set of rational, non-zero rationals. Then this will implies 2 times A is equal to A is 2 times E times A, and which implies your identity should be 1 by 2. Okay.
Excuse me,
So
sir.
this implies,
Excuse me, sir.
yes.
I'm sorry, I had unstable internet. But uh, um, from which week are these questions from?
Uh, from which?
From which week are these questions from?
So this is assignment 1.
Oh, but the assignment one is different, right?
Assignment
The
1 is
first
different.
question was different. The ones that we submitted.
Okay, so I have taken it from last year's assignment. So maybe they have changed it a bit.
Okay, sir.
There won't be many changes, but yeah, you are right. There might be slight changes. So maybe after this, I can just take it from the website of this session.
Okay, sir.
I don't think there will be many changes, but yes, there are changes. So, okay, so we will take from the current assignment 1 of this year uh, after finishing this question. Is it fine?
Okay, sir.
Okay. So, there the problem is just rationals under multiplication. The first problem is uh, set of all rational numbers under multiplication. And this slight change here, it's set of all non-zero rational numbers under this multiplication by scaling it with 2. So not much difference is there, but we will see that question also. Okay. So clearly, uh, identity exists, right? And what is the inverse? Can you now just tell me? It's good. Now you have different set of questions, so you can try here if you have not seen them before. So what is the inverse? Can anyone tell me?
I'm sorry, can you show the question now?
So the operation is A star B is equal to 2AB. So we have calculated the identity, which is just 1 upon 2. So let A be inside this set and B belongs to this B such that A star B is equal to identity is equal to B star A. So that is what we require from an inverse. Now from the definition, can you just tell me what should be the B? E
1
of
by 2.
1 by 2, just 1 by 2,
No, 1 by 2 B or A. Okay.
1 by 2 A, right? So this is 2AB or 1 by 4, right? This is 1 by 2 and this is 2BA. So that implies B should be 1 by 4A, right? So for any, this is again belongs to Q star. Since A is non-zero, so this is well defined. So for any non-zero rational, we are having B equal to 1 upon 4A for a given non-zero rational A to be its inverse under this operation. Okay. This implies inverse also exists. Inverse exists for all A belongs to Q star, right? And thus, uh, set of all non-zero rationals under this operation is a group. Now, can you tell me, let me ask a very relevant question. What if we have A star B to be lambda times AB for some lambda belongs to Q star? Can we still say that it will be a group?
Yes, sir.
Yes. So, uh, then again, Q star with this operation forms a group.
Lambda is non-zero, right?
Non-zero, that's what we are taking. Na? If you take zero, then it will be just A star B is zero. So how will you have inverses and even identity element will be a problem. So lambda we are taking to be non-zero, and anyway we want this number to lie inside our set, right? So if you take lambda to be zero, then this number will be zero, but zero is not inside our set. So it won't be a binary operation in fact.
Yes, sir. Got it.
So now for this, what will be the identity?
1 by lambda.
1 by lambda. Very good. Put the identity element. 1 by lambda and inverse of an element A belongs to Q star is what? Then you
1
just
by lambda square A.
1 by lambda,
Lambda square A.
lambda square A. Very good. Okay. So not just multiplication of non-zero rationals, but some scalar times multiplication of non-zero rationals also forms a group. Okay. So now, second problem is whether the set of all integers under the operation given by A star B is just A plus B minus 1 is so forms a group. So in the first problem, what we have a set which forms a group under multiplication, that is the non-zero rational numbers, and we just scaled the multiplication rule by some non-zero integer and non-zero rational, and then verified that it still forms a group. Now here what we are doing, we are having a set of integers. Now set of integers forms a group under usual addition, right? So if we have just A star B to be A plus B, then it forms a group. Now we are scaling that addition operation with some integer and asking whether it forms a group. If it forms a group, then we can ask what about A plus B plus C for whether that forms a group or not. So first let us check whether this forms a group. So again, binary operation is clear because A star, if A and B are two integers, then A plus B minus 1 is also an integer. So binary operation is clear. You can also check that this operation is also associative. So let me now solve part B. So star is an associative binary operation. Now, what is the identity element?
1.
Identity element is 1. Very good. How you come out? You did the calculation or you just guessed?
I did the calculation.
Okay. So let me check if you are correct. Then I will also tell you one trick. So let E belongs to ZB such that A star E is E A, that is E star A for all A belongs to Z. This implies this is A plus E minus 1 is A, and this is E plus A minus 1. And from here A and A will cancel, thus E has to be 1. So you can also make a guess from the previous observation or from the previous example. So here we have have the multiplication operation, and we scaled the usual multiplication by some scalar, right? And what identity we get? The usual identity divided by that number, and which is also the multiplicative inverse of this uh, scaling number that we took, right? Here also same thing is happening. So we scaled the usual addition operation by minus 1, right? And then what is the additive inverse of minus 1?
1.
1. So 1 here is coming out as the identity. Okay. So there both problems are mathematically, I will say, same. Only thing we are doing it in different setups. Okay. So inverse also we can calculate similarly. Let A belongs to Z and B belongs to Z be such that A star B is E, which is B star A. This will implies A plus B minus 1 is 1, and that is B plus A minus 1. Okay. So here what B will be? B will be just 2 plus A, right? Now again you can see there what we have 1 upon lambda square of A. So this is basically lambda square A inverse, you can say, right? So in group theoretic sense, if our lambda here is minus 1, then what will be minus 1 square here? What is the operation? Addition, right? So this will be just 2 times minus A plus A, and I hope I am doing it correctly. It should be minus A, right? 2 minus
Sir,
A
I
should,
think it's 2 minus A.
so 2 minus A should be there, right?
Yes, sir.
Okay. Now let's see in this set from here how we can guess. So in general, if the scaling is done by lambda, so we were getting the for multiplication lambda square A inverse. Now if we just change the multiplication operation by addition, then what will be this lambda square? This will be just 2 lambda. In general, this is lambda star A, and then its inverse. So here our lambda is minus 1, star is addition. So this will be 2 minus A, and again star is addition. So plus A, and inverse means taking the additive inverse, that is minus, right? So this will be minus of minus 2 plus A, which will be just 2 minus A. Okay. So again you can see that same both mathematically they have the same meaning. Only thing is we are just changing the multiplication operation by addition operation. Okay, so that's why this theories, this algebraic theories are nice. We can understand different algebraic structures through the same set of rules and statements, and these kind of things motivates you to read these structures as a nice theory. And so if we are dealing some problems with a group, then similar analogous statements would be true for another groups as well. Okay, so I did this just to make a correlation between the two examples. So again, this forms a group. Jets with star forms a group. Now, let's come back to problem third.
Thank you, sir. This is very interesting.
Huh? You
This, this is very interesting. Thank you so much.
okay? Thanks, Prerna. So now this should be easy. G is the set of complex number a plus bi such that 0 less than equal to a plus b less than equal to 100 under addition. So does it form a group?
It is not close.
It's not closed. So it's even not a binary operation. So that's why I told you that even if the in the groups is even in the statement, if it is given that with the indicated binary operation, first thing one should do is to check whether the binary operation is there or not. Okay, so not a binary operation. Can you just quickly give me an example?
Take both. So take A to be 100 and B to be 0, and for some other example, take A to be 0 and B to be 100.
Yes, or you can simply forget this. Just write say 51 plus 51. This is your first one. This is your second one, right? So what I am saying, whatever example you gave, that is also fine. And what I am saying that even if we don't consider this complex part, so this question, this problem is not even valid for the real numbers. For real numbers also, this won't be a binary operation. And from there itself, one can get. So if you don't want 51, then maybe 52, some other number. So this won't be inside G. Clear? So even if I replace this, G is the set of real numbers A such that 0 less than A less than equal to 100 under addition, then also it is not true. So this is even more. Okay. Yeah. So now uh, G is the set of all 10 cross 10 matrices with integer entries whose determinant is between -1 and 1 under matrix multiplication.
Again, this is not a group. If determinant of some matrix is 0, then it won't have an inverse.
Very nice. So this is uh, not closed. Uh, so if determinant of 0, then what will be the problem?
Won't have an inverse.
Don't have an inverse, right? So clearly I can say that 0, 10, you know this notation, right? Which is just 0, 10 cross 10, 0 matrix. Or simply I can write matrices with determinant equal to 0 belongs to G, but these matrices don't have an inverse. Okay. Thus, this doesn't form a group. Now, maybe we can move to the original assignment. Yeah, by the way, thanks for the clarification. I was just copying it from last year assignment, but it has been changed. So let us start with this year's assignment 1. Yeah. So which of the following sets with the indicated binary operations are groups? First one, all rational numbers under multiplication.
No, 0 doesn't have an inverse.
Good. So 0 belongs to G, but 0 inverse I does not belongs to G. So this is done, and I will just mark cross here. G is the set of all integers and the operation is given like this. So this is what? A plus B whole square. So does it form a group?
This is not associative.
This is not associative. So let us see this. So binary operation is fine, right?
Mm.
So binary operation part is fine. Now what about associativity? Good. Um, okay. So A star B star C. Simply write this. What it is? This is just A plus B whole square star with C, which means A plus B whole square plus C whole square, right? And this will be A plus B raised to 4 plus C square plus 2C times A plus B whole square, right? And the other side is A star B star C, which means A star B plus C whole square and then A plus B plus C whole square, that will be just A square uh, B plus C raised to 4 plus 2A B plus C whole square. So why they won't be equal? Can you just tell me one term which is here but that is not here?
A power 4 is there in the first one, but it's not there in the second one.
Very good. So this implies A star B star C is not equal to A star B star C in general. Good. Generally, people assumes associativity is always there, but that is not the case. And here, one such example we are seeing. So, star is not associative. So this is also not a uh, group. Uh, yes. So what about the third part?
Third one is a group.
It's a group. G is a set of complex numbers with absolute value 1 under multiplication. So you know what is absolute value?
Yes, sir.
What is the absolute value of a complex number Z, which is say A plus iota B?
Root of a square plus b square.
Root of A square plus B square. Good. It belongs to C. Uh, absolute of Z, which is same as we denoted by mod Z, that is root of A square plus B square. So this is basically the set of numbers which lie on the unit sphere. Okay. Uh, so if you consider see the complex plane, then all points on the uh, sphere of radius 1 with center to be at 0 means, so if you have this complex plane where the real part is this x and the imaginary part is say y, and then this is the center 0 0 which denotes the number 0. So these are all the numbers which lie on this unit sphere of radius 1. Okay. So, uh, so if you are interested more in mathematics, then you will learn that there are very few such geometric figures which actually gives you groups. So this is unit sphere, but in general, the groups are not represented by such geometric figures. The symmetries of geometric figures forms a group, but here uh, each element of the group is a point on this circle, right? So that's also one point. Now let us see whether the elements forms a group. So clearly, binary operation is there. Root of a square. Uh, so this is just a subset of complex number, but this is because mod of Z1, Z2 is just mod of Z1 times mod of Z2, right? So if this is of unit 1, this is of unit 1, then this will also have what to say, absolute value 1, right? So binary operation is done, and associative because multiplication of complex number is associative, right? Associative, and this is since multiplication of multiplication of complex numbers is associative. Okay. Now, what about identity?
It's one.
So one belongs to G, and hence the identity is also there. And inverse for any Z inside C Not C. I should write for any Z belongs to C with mod Z equal to 1. Z inverse is what? Z inverse is just 1 upon Z. In general, complex numbers have don't have this inverse. They also have some modulo part, because this inverse in complex number doesn't really make sense, I guess. Inverse is fine actually. Conjugate, for conjugate, you need modulus to be in picture. So this will be the inverse. Now, how to write this inverse in terms of A plus iota B form?
A minus iota B.
You just
A minus iota B.
A minus iota B. And how you are coming with that? You just multiply both side by conjugate of Z bar, and this will be Z bar mod Z square. Since mod Z is 1, this will be just Z bar. Okay, which is A minus iota B. So again, since A plus iota B has modulus 1, which is root of A square plus B square, Z bar, which is A minus iota B, will also have modulus 1. So this again uh, belongs to G, since Z bar, modulus of Z bar is same as modulus of Z. So if it is 1, then it has to be 1. Okay. So this forms a group. Now, what about the last one? Set of all invertible 3 cross 3 real entries with multiplication.
Group.
This is group. This is just GL and R. GL 3R in fact. Okay. So I'm not checking the details. It's a very well-known example. So I leave it to you. Okay. It's very easy. Means it's if two matrices are invertible in real entries, then their product is also invertible. Of course, the real entries will be there, because for getting inverse, what you do, you just take the uh, matrix of cofactors, the adjoint, and then just divide it with the determinant. So anyway, at each entry, you will just get the sum and products of real numbers, which is again a real entry. So it is closed, and uh, identity is just the 3 cross 3 matrix identity. Inverse is just the matrix inverse. Matrix multiplication is always associative. So that will do the job. Okay. Okay. So now maybe we can move to the second question if it is fine.
Yes.
Okay. Let G be a group, and let X, Y, Z, W belongs to G be such that they satisfy this relation. Which of the following statement is always true? Any guesses?
1 and 3.
1 and 3. Why?
Um, just doing the calculations.
Why not the other options? So let me first see y of a is there. So clearly you have x square y minus cube z square w to be x minus cube y w inverse. So you just need to do a little bit of shifting of variables and you will get. So we want y cube to be at one side. So we will take this. We need to take this y here. But for that, we first need to multiply this x square here. So it will go as x minus 2. So y cube z square w to be x minus 2, which is x minus 5 y w inverse. And then this w also we want to shift it here. And this will be y minus q z square x minus 5 y w minus 2. And then take this z also this side. This will be y minus q x minus 5 y w minus 2 z minus 2. Now we want y cube, so we will take the inverse. Y cube will be just x minus 5 y w minus 2 z minus 2 whole inverse, and that will imply y cube is z square w square y inverse. Just take the inverse. So inverse of some numbers a b c d inverse is just take inverse from the right side, d inverse, c inverse, b inverse, a inverse, right? So we'll just do that. So this will be y inverse, and then you have x raised to 5. So of course, first is correct. But why B is not correct? So B, if y cube is this number x, so it is just the reverse of this particular element, right? You just write everything in the reverse order. Also, the power of z is changed here. There is more tricks. In, so this is w square. Then by part 1, so it is any x, y, z, w or any elements of any group G, and for that, if this is true, then this must hold, right? So if it is not true, then we need to find a counter example. Then by part A, y cube is already equal to this, z square, w square, y inverse, x5 is x5, y inverse, w square, z minus 2. Now, can you give me an example of a group and x, y, z, w such that this is not true, provided
Some
that this is true?
non, some non-abelian group might work.
Some non-abelian group. Okay. So take some non-abelian group. So for your, so we already have this thing. We should not disturb this identity. This is always true. This one, right? This one, or we have just copied it here, so you can also see from here. This identity should be true, but this should not be true. So what if I take Z to be identity? Then it will simplify, right? Some simplification will be there. So if I take, say, I'm just making a guess. So if I take Z to be identity, this will be just X square, Y minus cube, W, and X minus cube, Y, W inverse, right? And now, can we have a group for which this identity holds? Now here also, if I apply Z to be identity, then what this will become? This will be just W square, Y inverse, X5, and this is X5, Y inverse, W square. Somehow we need to show that this is true, but this is not true. Can we do some more uh, trick? Some more like specialization will help us or not? For example, what if I put Y to be identity as well? This will vanish, this will vanish, and we will have X square uh, W to be just X minus cube W inverse. And here also, if I remove this, then this will be W square X5 and uh, X5 W square. Can you just now produce some counter example? So what this gives you? This gives you X raised to 5 is uh, so if I take this there, this will be X5 is same as W minus 2, right? I am just multiplying it both side from left by X cube and then from right by W inverse. So this will give this. Now, if I put here using this identity, this will become uh, identity, and this will also become identity. So that means we are over specifying the problem. So our assumption that Z equal to identity and Y equal to identity should not be there. So we need to do it without putting that much specification. Maybe we can put some other variables to be identity and then try the same thing. Okay, so you uh, just see most probably you will get a counter example in the first non-abelian group, that is S3 itself. Only thing is you need to vary your X, Y, Z and W. I can do that, but that will unnecessarily take the time and we won't be able to finish some other problems, right? So I'm leaving it to you. You just check that what I believe that in S3 there should be elements X, Y, Z, W for which this relation holds, but this relation will fail. What if we put W to be identity? Uh, Here, in fact, I think the sum is uh, what is the sum of indices? Here it is plus 2. Here it is minus 3. And here it is 4 9 plus 8. What if we put everything to be same, x, y, z and w? Is it working? So I'm just try to get some counter example, because if we want to say that this option is wrong, intuitively it seems to be incorrect for some non-abelian group, but it's good to have some counter example in mind. So if everything is same, then this will be x square, x minus cube, x square and x. So this will be just x square in the left hand side. Here sum of power is 2 minus 3 minus 1, then plus 1 and plus 1 2. And what will be here? Here you will have x minus cube, right? So this will say that x5 equal to 1. And here if we do the same thing, everything we make it equal to x, then it will be x4, x9, x8 is equal to, this will cancel out. This will be x4, right? Right. And that will give you x4 equal to 1. So here is a counter example. Simply you can see that, see here, it is not saying that this should hold for all elements of the group. It's just saying you pick a group G for which there is just a uh, a collection of 4 elements for which this relation is satisfied. Then which of the relations must be satisfied? So you just need to pick a pair of, for which this relation holds, but the other one doesn't hold. So now, can you just tell me the counter example? If we take G to be Z mod 5Z, cyclic group of, I hope you know this, cyclic group of 5 elements, and take any element which is of order 5. So then you will have this x5 equal to 1, and x, y, z, w, everything is just 1 bar. Then you can check that the first relation will be satisfied. So what is this x square, y cube, z square, w? X square minus y cube, z square, w will be, this will be 2 bar. Then, so everything is same. So you will just have, just need to calculate the sum of powers. 2 minus 3 minus 1, then plus 1 and again 1. So this will be 1 bar square here in addition. So this will be just 2 bar. And what will be the RHS? RHS is again x minus cube, y w inverse. So this is minus 3, minus 4 and 1 gone. So it will be just minus 3, which is minus 3 bar and which is 2 bar, right? So the given condition holds. This implies x square y minus cube z square w is same as. So Prerna, you were saying some non-abelian group will work, but we have actually produced an example of a abelian group, right? In fact, any group which has a element of order 5, for that group, this will work, because we saw, right, if we are putting everything equal to 1 identity, then this relation produces x5 equal to 1, and this relation produces uh, x5, x4 equal to 1. So if an element is of order 5, then x5 equal to 1, but x4 cannot be equal to 1. So any group which has a order element of order 5 will give a counter example. So we have in particular taken this, but so let me just circle this also and give some second. But from, or let me just give it one. First relation is already in the problem. You have z square w square y minus q1 x5 equal to x5 y inverse w square z minus 2. This will implies for for x, y, z, w equal to 1 bar. This will implies simply we are in abelian setup, so we can add powers 4, 9 and just 1 minus, so it will be 1 bar 8 and this will be 5, 4, 6, then again 4. 1 bar is 4. What it is? This is we are under modulo 5, right? So this will be 8 bar and 4 bar, which implies this will be 3 bar is same as 4 bar, which is a contradiction. So B is not correct in general. See, intuitively we might be getting the answer, but to in maths many times intuitions fail. So until unless we have a counter example, we should not say with full confidence that this option is correct or that option is wrong. In most of the cases with such examples, definitely your intuition will work out. If something you are not getting directly, then definitely that will not be true. But it's better that you produce a counter example. That will not only assure you of your intuition, but also will uh, improve your skill of producing counter examples, because producing counter example is as good as proving something. So always try to produce counter examples if you believe that something is not true. Okay. So first is correct, but second is not. And uh, similarly, I think you can do the other two parts. So I'm just quickly writing the solution. So from this x square y minus q, z square w, s square y minus q, z square w equal to we have uh, x minus cube y w inverse, x minus cube y w inverse, and this will implies what we need in terms of x5, right? So in terms of x5 we need, so we just take this x cube here, x, and this will give us x5 y minus cube z square w is y w inverse, and rest of the things we will take this side. First we take w inverse, then z, and then y. So this will be y, w will come here as w inverse of w minus 2, then z minus 2, and y cube. So is there any option with this choice? I think C itself is there. So, Oh, D is there, so C is not necessarily be true, but D has to be true. So let me just change this option to D. This implies D is correct. Right? We are getting the same expression yw minus 2z minus 2 y cube. Right? Now, what about C? So for C, y should commute with z and w, right? So if we are under abelian setup, definitely this will hold. So what we should do, we should be taking some non-abelian group to produce a counterexample. C, if so, here x5 is given to be y4 w minus 2 z square. Then by part D, what we should get? So this should be equal to this. That will implies y4 w minus 2 z minus 2 should be equal to y w minus 2 z minus 2 y cube, right? Now, what relation this will give? One y you can cancel. This will imply y cube z minus w minus 2 z minus 2 is same as y2 z minus 2 y cube. So y cube should commute with y with w and z. Now, clearly if y belongs to if y belongs to center of G, then this holds. So we need a non-abelian group for which there exists xyz belongs to G such that the above relation is, or the above relation does not hold in G. So can you quickly make a guess which group we should be looking for, or which is the ideal group to look for at the first step? Which is the first non-abelian group you know?
S3.
S3. And what elements we should, what kind of element we should take? So y should not be in the center, or more precisely, we can say y cube should not be in the center. Even if y cube is there inside the center, then also this will hold. So in S3, you have an identity element, 2 cycles and 3 cycles. What should be the ideal choice for y cube?
1, 2. It doesn't belong to the center
Right.
anyway.
So take G to be S3 and Y to be a 2 cycle, because if we take a 3 cycle, then this will be identity. Or if we start with identity, this will be identity. So that doesn't help us. So let Y be just 1, 2. And again, if W and Z both are inside center, then also this won't help us, right? or uh, W square, Z square, both are inside center, then also we have a problem. So we should look for W and Z such that both simultaneously are not inside center. Both squares are simultaneously not inside center. So one of them we can definitely take to be identity. I think that won't uh, create a problem. But other thing we need to take such that its square is not inside. So if I take say W to be identity, then W will vanish from here. We just have y cube z minus square is z minus square y cube. So y cube is not inside center. Now we need to take some z such that its square does not commute with y cube. So what should be the choice for z?
1, 2, 3.
1, 2, 3. Very good. So we need to take something whose square does not doesn't belong to the center. So see, I am also constructing counter examples right now. So constructing counter examples is very crucial. It will help you in understanding the theory uh, in a very nice manner. So now you can check what is y cube y w y cube w minus 2 z minus 2. So y cube is taking cube 3 power of 1 2. So after taking 2 power 1 2 vanishes. So you just have 1 power left, right? So it will be just 1 2. W is anyway identity, so it will vanish. So this is just identity. And what is z raised to minus 2? So it has order 3, right? So z minus 2 is as good as z1. See, if some element has order 3, then a minus 2 is same as a cube minus 2 because a cube is identity. So this will be just a, right? So we can just simply write it as it is. Now, what is this element? 1 goes to 2 and then 2 goes to 1. So 1 is fixed. 2 goes to 3. 3 is not here. So 2 will go to 3. 3 goes to 1 and then 1 goes to 2. So this is the cycle 2, 3. And z minus 2, w minus 2, y cube. So we may fail also, but at least we are going in the right direction. There is a possibility that we should be at the right example. So z minus 2 is 1, 2, 3. Uh, Again, z minus 2 is 1, 2, 3 raised to minus 2, which is 1, 2, 3 itself. This is identity. And y cube is just 1, 2. So it just, if 1, 2 commutes with 1, 2, 3, then we are gone. But in S3, we know that 1, 2 does not commute with 1, 2, 3. So let me just write it. So 1 goes to 2, 2 goes to 3. So 1 is 3. 2 goes to 1, 1 goes to 2. So it is fixed. And 3 maps to just 1. So this is 1, 3. So they are not equal. Can we say that we have produced a counter example?
Yes, sir.
Wait, but we have not checked the initial condition given to us.
Oh, okay.
This one, right? So we should also check this. If this is not happening here, then I will leave it to you to find the counter example. Okay. So we also need to check the uh, the condition x square y cube y minus cube z square w. Yes. x square y minus cube z square w. What is in the RHS part? X minus cube y w inverse. X minus cube y w inverse. So for what we take y to be 1 2, w to be identity, and z to be 1 2 3. Let me now give it this condition. Second implies, so w will vanish. We don't have anything for x, so we will keep x as it is. So y is 1 2 minus cube, so this will be so after taking square, this vanishes. So this will be just y inverse, which is itself 1 2 z square. So this will be 1 3 2, and w is identity, so we need not to worry about it. X minus cube is uh, as it is. Y is 1 2, and w inverse is identity. So w inverse is not playing any role. So now what is this? X square. 1 goes to 3. Uh, 3 is here, so this will come as it is. 3 goes to 2, 2 goes to 1. So 1 is going, and 2 goes to 1, 1 goes to. So this will be 1 3, x minus cube 1 2. So this will implies x5 is 1 2 1 3 inverse, but 1 2 is 1 3 inverse is just 1 3, and which is 1 goes to 2, 2 goes to, sorry, 1 goes to 3, 3 is going to 1, 1 is mapping to 2, so 3 2, 2 goes to 1. Now, if we get an element in x3 such that x5 is this 1 3 2, then we are done, right? Because we need to find a choice of x, y, z, w such that this condition holds, but this condition doesn't hold, right? So in the previous condition, we don't have any restrictions over x, but here we are having x in the relation. So if this condition holds, then x should be such that x5 is equal to 132, right? So does there exist? So let me just formally write the question. So if there exists x belongs to S3 such that x5 is 132, then we are done. You got the point? Because for our chosen choice of y, z, w, we have already shown that the previous condition doesn't hold, but this condition is giving us x5 equal to 132. So if x5 is equal to 132 for any x, then with that x and our chosen choice of y, z, w, we are done, right? So can you tell me any x inside S3 for which x5 is equal to 132? Someone has written. Okay, no issues. So any guesses? See, we also know that in S3, x6 is equal to identity, for all x, right? So can we use this? So axis is just, this is just x inverse. In S3, x5 just means x inverse because axis is anyway identity. So
Sir, no.
x is just the inverse of 132, right? So x is just 132 inverse, which means 123, right? So that implies for x equal to 123, y is equal to 12, z equal to again 123, and w equal to identity. Uh, the relation, this was our second relation, right? The relation second holds, but x5 is not equal to. So we were doing all these things to prove that C is incorrect. And C says that x5 is y4 w minus 2 z minus 2, right? So this doesn't hold. Y4 w minus 2 z minus 2. So if you have any doubt, you can still verify this relation again. X5 will be just taking fifth power of this 123, which will be just 132. Y4 will vanish, it is identity. W will vanish, it is identity. And Z is Z minus 2 is again same. So this part is inverse of 123, that is 132, and this part is just 123. So they are not same, but for these values of x, y, z, w, our initial conditions hold. Initial condition was this, so this condition hold. So uh, that's it. So this particular choice of x, y, z, w, and g equal to s3 works. So of course we are taking here g to be s3. Okay, that is inside the underlined assumption. Okay. So any
Yes, sir.
doubt in that?
No, sir.
Okay. This implies the option C is not correct. See, for NPTEL exam, it's okay if you are getting some intuition and you just tick mark, then it's fine because you have time constants. But in general, if you want to learn the subject, then you should be able to produce counter examples to support your intuition. That will help you in later stages of your life. If you are if you want to pursue mathematics further. Okay, so let
Okay.
me paste problem 3. If there is any doubt in this problem, then you can ask. So we need to choose the correct statement. If G is a group containing 4 elements, then X4 equal to identity for every element X belongs to G, where identity denotes the identity, E denotes the identity element of G. So is it true?
Yes, sir.
So in general, X raised to order of G is identity. right? That also we have seen. So this is correct. So in fact, for a finite group, for a finite group G, x raised to size of G raised to is equal to identity for all x belongs to G, right? So size is 4. So this will be true. For a group containing 6 elements, x cube is equal to identity for every element x belongs to G.
This is false.
This is false.
Taking this 3,
Why?
1, 2 is not equal to E.
Right. So for G equal to S3, 1, 2 raised to cube is 1, 2, which is not equal to identity. Okay. Now what about the third one?
Third one is true. We can
Why?
take Z.
We can take Z and write the cyclic group of n integers. Sorry, n elements. For every positive integer n, they register non-abelian group which contains exactly n elements.
This is false.
This is
We
false.
know
Why?
that for any group of order less than or equal to 5, the group is always abelian.
Right. So for n less than equal to 5, any group of any group with n elements is abelian. Good. So maybe we can move to the next problem then. Which of the following are true about Sn, the symmetric group in n letters? We know E denotes the identity of Sn. For every positive integer n, Sn contains exactly n factorial many elements.
This is
1
true.
is
This is, so there were two voices. Uh, so is it true?
Yes,
yes,
sir.
first one.
First one. What is the proof?
So, um, suppose there are n elements. Um, so we consider all possible mappings from every element to the same
All
set.
positive mappings. Positive mappings is or just mappings, right?
All bijections.
All bijections, right?
So for the first element, there are n possible mappings.
And
So
possibilities.
yes.
Uh,
So um, so suppose it's mapped to one of the elements, then we consider the second element. Then it has n minus 1 possibilities, and we can keep doing this. So the total number of bijections possible will be n into n minus 1 and so on. That would just be n factorial.
Very nice. So for first one, we have n choices. So say, so these are just uh, so for first element, there are n choices. For second element, there will be
n minus 1.
there will be n minus 1 because first one is already, one choice is being fixed for the first element, right? This is, so first of all, we should understand that size of Sn should equal to the number of bijections on a set of size n, right? So this is the key point. And for that, for first element, we have n choices. Second element, we have n minus 1 choices. And similarly, for any ith element, we have for some ith element, there are n minus I minus 1 many choices. For the nth element, there will be just one choice. This implies there are total n times n minus 1 dot dot dot. Some for some I, there will be this, and at last it will be just n minus 1, which is 1 only. So there will be, this number is equal to just n factorial. These many choices, which implies size of Sn is n factorial. Good. I am happy that you know the proof. Okay, first one is correct. Second one, for every positive integer n greater than equal to 2, Sn contains an element x such that x is not identity and xy are equal to identity.
This is true.
This is true. Why?
Just consider the permutation which switches exactly two elements.
Right.
That's
So
true.
we can simply take x to be the element 1, 2. No, you were saying consider the permutation group which has two elements.
The permutation which switches only two elements.
So the permutation in which just two elements are moving. Okay, so any permutation of order 2, and such a permutation always exists for any n greater than equal to 2 in Sn. So that's why for any Sn, there is just an element of order 2. Third one, Sn is abelian for every positive integer n.
This is false.
This is false. So this is because Sn greater than equal to 3 is non-abelian. Because S3 is non-abelian and S3 is sitting inside any Sn for n greater than equal to 4. So this is non-abelian. Now, every element x belongs to S3 satisfies x square equal to 1, I square equal to identity. That is also false, right? Take
Yes, sir.
simply a 3 cycle, x equal to 1, 2, 3. For this, we don't have x square equal to identity. Okay. So if it is fine, then maybe we can move to the next question.
Yes, sir.
G is GL2C, the general linear group of 2 cross 2 matrices over complex matrices, which means just the group which contain 2 cross 2 invertible matrices with complex entries. We need to choose the correct statements. G is a group.
That's true.
That is,
Yes, one right.
uh, yes, you are saying something, Bahadur? There is some noise. Okay, good. So this is a group. I'm not giving a proof, but it is easy. If you have two matrices, invertible matrices, then the product is again invertible. So binary operation is there and identity is there, and inverse of an invertible matrix is again invertible. So and associativity is there because we are in multiplication of matrices. There is not much to do. Everything you already know. Is it an abelian group?
No.
No. Why?
Consider two matrices A and B, where A is 1, 1, 1, 2,
Right.
and B is 1, 1, 1, 3.
1, 1, 1, 3. What will be their product? Is
AB will be 2,
2,
4, 3, 7.
4, 3, 7, and
BA will be 2, 3, 4, 7.
this is 2, 3, 4, 7, right? Which is not equal. So this is not a abelian group. Are both of them invertible? Right. It has determinant 1 and it has determinant 2. So both of them are invertible. Okay. Okay. So is G a finite set?
No.
No. Why?
Um, okay. Consider the set of matrices R times I. Um, they are uncountable. So
R times I. So um, that means just R 0 0 R, right? Such that R belongs to where?
real numbers
A real
or
number.
even rational will work.
Or even
Non
what if I just take even if I can take non-zero complex numbers, right? If it is non-zero, then if R is non-zero, then R square will also be non-zero, right? And determinant is just R square,
yes.
right? So we can simply take this. This is an uh, this is an infinite subset of G. For every integer n greater than 2, there exists a matrix A such that A is non-identity, but n is identity, where I is the identity matrix. What about the D part?
D is true.
D is true. What is the matrix?
So it's same as the identity, but the first element has nth root of 1. So um, taking
Okay.
the whole matrix power n will give I.
So take some Wn 0, 0, 1, right? Take A equal to this, where Wn is the nth root of unity. In fact, you can take the nth rotation matrix as well. Cos sin cos theta, sin theta minus sin theta, and cos theta. That is the rotation matrix, right? If you take nth rotation matrix, means you take theta to be just 2 pi by n. So since it's a rotation matrix, if you rotate the element n times, you are supposed to get identity. So an will also be identity. So that is also one choice. But since you have come up with your own choice, so I will go with that. Okay, good. Now, if it is fine, then we can move to the next problem, which is also the last problem of this assignment. By the way, what was the last date of submitting assignment 2? Is it already over or?
Yes, sir, it's already over. It was on 6th August.
Okay. And assignment 3?
Tomorrow's the deadline for assignment 3.
Okay. So in the next class, maybe we can discuss both the assignments. Okay.
Okay, sir.
So let's first finish this one. Time permits, then we can do some other problems as well. So here ng denote the least integer such that x and g equal to identity. Basically, ng is just the order of the element x inside the group G. Then we need to choose the correct statement. So if G is S3, then ng is between 1 to 2. Is it correct?
No, sir. Consider 1, 2, 3.
So all questions are basically means I more than half of the questions are solved if you know what is S3 till now, I guess. So again, we know that in S3 there is an element of order 3, so that won't satisfy this. In S3, ng is between 3 to 5.
That's also false.
That is also false because we want the least integer. So if the least integer part is not there, then this would have been true. Because for order 2 elements, if you take power 4, then also it's identity. So 2 cycles would have satisfied this. Also 3 is there, so 3 cycles would have also satisfied this as well. And for identity also, if the least integer is not there, then it would have been true. So the least integer part is also crucial. Okay. So take x equal to 1, 2. If G is a group of 3 elements, then ng equal to 3.
That's true.
That's true because we know that x raised to order of G is always equal to identity. And what about the fourth one? If G is a group having consisting of 6 roots of unity, then again it's a group of order 6. Thus, and G is equal to 6, right? Because you have the primitive root of unity for which the order is 6. So the least part is there. Uh, one, one, one correction, sorry. I said here the least part is uh, playing role for uh, order 2 elements, but here we want this ng to be the same for all elements, right? So we cannot take ng equal to 4 for 2 cycles and ng equal to 3 for 3 cycles. We need to have a uniform 4, uniform integer. So even if this least thing is not there, still this option is false. Okay, so just a slight correction. So because we want a uniform integer. Here, ng is 3, that is okay. And here also this is fine. Okay,
Sir,
so yes.
what, uh, what if I take NG to be 0? That would, that would be sort of the least integer, right?
See, for least, we we expect that it should be positive.
Oh, okay, so.
Okay, so if positive is not there, then uh, you can also go to the negative direction, right? We're just
Yes.
saying least integer, right? So you can also take uh, -3. -3 will also work. -6 will also work. Ideally, they should have mentioned least positive integer, but even if it is not there, then the underlying fact is it should be positive. Otherwise, you can go infinitely uh, behind, right? -3 will work. In this case, -6 is working, so -12 will work. Any multiple of 6 will work. So the least number doesn't exist if you don't assume it to be positive. Okay.
Okay, sir.
But anyway, it's a good question. Uh, they should have mentioned positive here. Okay. Um, Now, if you have any questions to ask, or if you have any issues in assignment 4, then also you can ask. Otherwise, I will randomly pick questions from assignment 4 and solve. Assignment 4 is what we are supposed to discuss now, na? Right. So it's
Sir, do you mean the practice assignment 4?
from practice assignment, right?
Sorry, sir, I haven't yet solved the problems from practice assignment 4.
Okay, so you do it next time maybe. We have still have some time, so I can pick some problem and then discuss. Or you can tell me any problem from practice assignment which you want me to discuss, then I can do that. There are just 5 problems. Do you have access to the practice assignment?
Yes, sir.
So maybe you can check if you have any problem in that. The others can also check and tell me if they want me to discuss any particular problem from practice assignment, then I can do that now.
Sir, there's still some lectures that I need to uh, go through, so I don't have any doubts right now, but maybe if
Okay,
someone
okay.
else has the doubts that can be
If anyone
discussed.
else want me to discuss something, then so the first problem I can just tell. The first problem in practice assignment ask that for a finite group of even order, there exists an element of order 2. So I think that has already been discussed in one of the lectures. So you just check it and let me know. If it is not there, then I will tell you the proof. But I believe that it is already there in one of the lecture notes. Or I can tell you the hint. So if it is a group of even order, so definitely there is one element of order 1 and there is a unique element of order 1, right? That is identity. Now, if there is no other element of order 2, then for any element, for any non-identity element, A, A should not be equal to A inverse. Because if A is equal to A inverse, then A square is identity, right? So that means A is of order 2. So assume that there is no element of order 2 inside the group. So uh, for any non-identity element A is not equal to A inverse, right? Now, what you can do, you can make pairs of all non-identity elements, pairs containing A and A inverse. right? Because A and A inverse are different. So you take A to be a non-identity element. A inverse is not equal to A. You make a pair, separate it. Now you choose B, which is not A and which is not A inverse, and which is also not equal to identity. You can club it with B inverse, make another pair. Then you can take and you choose with and you start with any other element C, which is not A inverse, B inverse identity. Again, you can get C inverse, which is not equal to C. And similarly, all non-identity elements can be divided into pairs of size 2, right? That means how many elements are there inside the group? If the number of such pairs is n, then what is the size of the group?
It would be odd number.
That is an odd number. So size will be 2n plus 1. But we have the assumption that the group is of even order. So it's a contradiction. And why this is coming? This is coming because we assume that the group does not contain an element of even order. So the assumption is false, and thus there should be at least one element of even order. Now, since this it's a nice opportunity, so I give you a task that go and check something called Cauchy's theorem, which says that I think it's Cauchy's theorem only. So the statement I can tell, then you can maybe check it. For any finite group G, if a prime P divides the order of G, then the group has an element of order P. So this statement is a specific case of that uh, theorem. Here, what is P? P is 2. Because if the order of the group is even, then the prime 2 divides the order of G, and hence there should be an element of order 2. So what I mean to say that this statement holds in general for any prime P dividing the order of the group. And I think it is known as Cauchy's theorem only. You can just go and check if you are interested. You may not be able to understand the proof at this stage, although there are many ways in which one can prove Cauchy's theorem. And uh, if you are just following the lecture notes till now, then using that, you may not be able to understand the proof. But uh, you should know the statement because it's a nice opportunity to tell you a statement of such kind. So you should know. And whatever group we have seen till now, you can see this happening in those groups.
So can you repeat the theorem again?
So theorem says if G is a finite group and P is a prime, dividing the order of G, then there exists an element of order P in that group. So here G is a group of even order. So 2 divides the order of G. So there exists an element of order 2. So this particular problem is just a specific case of that theorem. Same holds for P equal to 3, P equal to 5, P equal to 7, and any prime dividing order of G. Okay. For example, in S3 itself, you can see there is its order is 6. So 2 and 3 both divides the order of G, and there are elements of order 2 and order 3. And that happens for any group G and for any prime P, any finite group G. Okay. Don't worry about the proof. Whatever proof you will find in internet, they might use something which is uh, beyond the literature that we have completed till now. But you should uh, appreciate the statement. That's what the purpose is. Okay. Now, second one is having many cases in practice assignment 4, the second problem. But third one is just a true false. So it asks it the problem says if G is a group and H is a normal subgroup of G such that the quotient group is cyclic, then G is abelian. So, are you guys familiar with the quotient groups?
No, sir, I need to go through it.
Okay, so if you are not familiar, then I can't proceed. What about the others? You know what is a quotient group? No answer. So mm, okay, then maybe you go and read lecture notes, and once you are familiar with the lecture notes, then maybe we can discuss assignment practice assignment 4 problems. In the next class, I think we can keep assignment 2 and assignment 3 for discussions, right? Is it
Okay, sir.
fine? Okay.
Yes,
So,
sir.
so revise assignment 2 and assignment 3 before the next class so that we have a nice interaction. If you have any other doubt, then you can ask. Otherwise, we can stop here.
I don't have any doubts, sir.
Okay. What about the other person? Venkat, you have any doubt? Oh, he left already. Okay. So maybe then I will stop here. We will meet on next Tuesday at the same time, 6 to 8. Okay. Okay. Bye.
Thank you, sir.